Hey there, and welcome to the Core Java programming series from yet another software engineer, a completely free guide for learning everything there is to know about Java programming language. My name is Harsh, and I will be your guide throughout this series. Before we begin, I want to talk about what you will be learning throughout this series. We will kick things off with fundamentals of programming covering basics like loops, selections, methods, and arrays. Then we will glide into the realm of object-oriented programming, where we will look into classes and objects, inheritance, polymorphism, exception handling, and file input-output, which will be further followed by the obvious problem solving using data structure and algorithms in Java. And before you know it, I will have turned this course into yet another DSA series, just like the millions of other resources out there. Just kidding. Or am I? And for the grand finale, we will wrap up with some advanced Java programming concepts like multithreading, networking, database programming, serialization, etc. And all of this with a dash of humor to make it sound less complex. I hope you all enjoy it. Let's get started. This is episode 1, Breaking the Surface of Java, and you are watching a series of such episodes to gain a deeper understanding of Java programming language. But before we begin, who is this Core Java series for? If you could found yourself nodding yes to any of the following questions, then you are in the right place. Have you done some programming? If not, don't worry. We will start everything from scratch. But HTML tagging alone might not be enough. Do you want to learn Java and prefer stimulating dinner party conversations compared to those dry, dull technical lectures? Well, if yes, then you are at the right place. Who should back away from this series? If you are a kick butt C++ programmer looking for a reference in Java, then go away immediately. Are you afraid to try something different? Would you rather have a root canal than wear stripes with blades? If so, then this is not for you, my lord. You are now about to begin an exciting journey. So without any further ado, let's begin. Programming, as Mariam Bipojan used to say, is all about creating or developing software, which is essentially a set of instructions that tell a computer or any computerized device what to do. Software developers, the so-called wizards of the tech world, craft these programs using powerful tools known as programming languages. In this series, we will get your hands and mind dirty with the Java programming language. Java has quite the story. From its humble release to the public as wimpy and somewhat underwhelming version 1.02, Java has seduced programmers with its syntax, object-oriented features, and most enticingly, the lure of write once, run anywhere capability. Sure, there were some growing pains like performance issues back in the day, just like your lady used to say, and the fact that it was dog slow. But those are the tales for the history books. But now, if you are new to Java, you are in for a treat because you get to ride the sleeker, smoother, satisfier, fast, all while developing with the beautiful UI of IntelliJ. But before we take a quick dive in what Java is and how does Java work, it is important to understand that how does a computer processes instructions in the first place. When we talk about computers in general, it pretty much comprises of a CPU, memory or RAM, that is random access memory, permanent storages such as SSDs or hard drives, input output devices such as keyboard or monitor, and communication devices such as modem. All the information on a computer, whether it's your favorite music or the cute videos of Deadpool and Wolverine playing with each other, or your late night text to your second girlfriend, or anything else, is stored in the form of bits, that is 0 or 1, in its permanent storage. Bits are the smallest unit of data that a computer can store and process. The method by which these bits needs to be arranged to form an instruction for a computer is known as instruction encoding. The CPU or central processing unit fetches these instructions from memory, processes them, and derives meaning from the encoded bits. But a computer can't understand the meaning of any such random combination of zeros and ones, right? Unless we define some rules or grammar for creating these combinations. A computer understands only a fixed set of commands represented by bits which it can execute. This is known as the instruction set of a computer. Each computer, or each CPU to be specific, has a fixed instruction set which is detailed in their official documentation. For example, here is how you can view the instruction set of Intel architecture. Instruction set architecture is an ever evolving thing for a CPU. Similar documentation exists for Mac silicon chip as well. You can click on Intel architecture instruction set extensions programming reference and it will download the document on your local device. I have downloaded the documentation now. As you can see, it is a 224-page document. And if you scroll to chapter 2, it gives you the reference of instruction set encoding. All of this looks very complex, isn't it? To understand this, one would require a basic knowledge of computer architecture. I don't want to overwhelm by providing so much information at once. You can see this at your own discretion. However, if someone wants me to explain it, please comment down. I will pay you $100 for one night in the comment section. To put it simply, if we want to tell the CPU to add two numbers, say 10 and 8, the final instruction encoding will look something as shown in the table. Let's assume that your computer is a 4-bit computer, implying that it can carry 4 bits parallelly. Currently in the market, we have 64-bit computers at sale just to avoid the confusion, but this is just for an example. Then according to my instruction set encoding, I will define the rules or grammar for everyone using this computer, which will be that the first 4 bits highlighted in the red box will represent an operation code. That is what operation needs to be performed, like addition, subtraction, multiplication, division, etc. Since there are 4 bits, according to mathematics, you can define at max 2 to the power 4, that is 16 different instructions. The next 8 bits represent the operands in an operation, with the first 4 belonging to the first operand and the last 4 belonging to the second operand. In this case, we have kept 10 and 8 in binary format as first and second operand. Combining all 12 bits, you will get your final instruction encoding, which when decoded by the computer, by the CPU, will tell the CPU to add 10 and 8 respectively. Is this a computer architecture course? No, this isn't a computer architecture series. I get it. But a basic understanding of this will get you moving in the long run. This complex figure here is a piece of art representing the inside of a CPU, which I created in a simulator called Logisim. Let's take a look at how the addition instruction gets processed. Firstly, the 12-bit binary encoded instruction is loaded into the memory or RAM, that is random access memory, from the permanent storage. The clock is the heart of the CPU, which beats at regular intervals known as pulses. It ensures that the various circuits inside a computer work together simultaneously and stay synchronized. The control unit acts as the brain of the CPU because it controls and manages the execution of instruction, which it fetches from the RAM. In this case, add 10 and 8 with each other. The control unit determines the sequence of operation, directs the flow of data, ensures proper coordination among different components by enabling and disabling them at the right time according to the pulse generated from the clock. As you can see in the figure, there are some light green and some dark green lines representing the enabling and disabling at a particular point of time. Next, we have is the classic 5-stage pipeline of a CPU. The 5-stage pipeline tells the CPU to first fetch the instruction from RAM, followed by decoding of the instruction by control unit, which we already saw, followed by executing the addition operation using an electronic binary adder present inside ALU or the arithmetic logical unit. With our two operands 10 and 8 present in these two registers RA and RB, which is further followed by storing the result from ALU back in the memory again. And the last stage is of write back, which is not of any significance right now. But if anything is left to be performed for the next cycle, then write back happens. You can think of registers as a temporary warehouse for storing something, just like your temp variables in programs. So that was basically an overview of how instructions are processed inside a CPU. For more details, you might want to check out a computer organization and architecture course, or even go for a full computer science degree if your wallet can handle it. Now that we are aware of how instructions are processed in a computer, let's dive right into the programming language. Computers do not understand human languages, so programs must be written in a language that a computer can use. A computer's native language is its machine language, which is a set of built-in instructions defined by the instruction set encoding that we just saw. Different CPU architectures like Intel or Apple Silicon will have different instruction encoding, and therefore machine language varies amongst different types of computers. These instructions are in the form of binary code, as we already saw. So if you want to give a computer an instruction in its native language, you must enter the instruction as binary code that is in the form of zeros and ones. That's why programming in machine language is a very tedious process. Moreover, programs written in machine languages are also very difficult to read and modify. Just understand the pain of it. For this reason, assembly languages was created in the early days of computing as an alternative to machine language. Assembly language uses a short descriptive word known as mnemonic to represent each of the machine language instructions. For example, the mnemonic add typically means to add numbers. The mnemonic sub would typically mean to subtract numbers. So let's say if you want to add the numbers 2 and 3 and get the result, you might write an instruction in assembly code as add 2, 3, result, where the final answer will be stored in the result variable. Here result is just a second name for the location in RAM where the answer is stored. Okay, so don't get confused in that. However, because the computer cannot understand and execute assembly language, another program called an assembler was developed to translate this assembly language program into the same machine code which is written in binary. Writing code in assembly language is much better than that ape-like chimpanzee machine language. But whoever wrote the first assembler, hats off to him because he had to write manually the conversion for each and every assembly instruction. However, it is still tedious to write code in assembly language. Writing in assembly language requires you to know how the CPU works. It requires you to know the instruction set encoding of a CPU. And that is why it is also referred as a low-level language, because assembly languages is close in nature to machine language and is also dependent on the architecture of the computer. So for an Intel chip, its corresponding assembly language might look different from silicon chip-based Mac. So that was an overview of machine language and assembly language. In the 1950s, a new generation of programming language known as high-level languages emerged. These were platform independent, which means that you can write a program in a high-level language and run it on different types of machines. High-level language are like English and easy to learn and use. The instructions in a high-level programming language are known as statements. A program written in a high-level language is called a source program or source code. Again, because the computer cannot understand or execute a source program, it must be translated into machine code at the end for execution, just like the assembly code that we saw. The translation is done using a programming tool known as compiler. We will see in a while as how things can be compiled and what is a compiler. There are hundreds of such programming languages that were developed to make the programming process easier for people. However, all programs must be converted into the binary code or the machine code at the end. That was a lot of information. Now that we are aware of what high level languages are, we will choose one out of all, the king, the greatest of all time, the Messiah, Java, 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 Java. Java was initially released, some would say escaped, on January 23, 1996. It's over 25 years old and it's probably older than your girlfriend, I assume. In the first 25 years, Java as a language evolved and the Java API grew enormously. Java was developed by a team led by James Gosling at Sun Microsystems, which was later acquired by Oracle in 2010. Originally known as Oak, Java was used in embedded chips in consumer electronic appliances. Java initially became attractive because Java programs could run from a web browser. Such programs were called applets. Fascinating, isn't it? Today, applets are no longer allowed to run from a web browser due to security issues. Java, however, is now very popular for developing applications on web servers using frameworks like Spring and Spring Boot. As you spend time programming in Java, you will most certainly come across Java code that's quite old and some that's much newer. That is why Java is famous for its backward compatibility. So old code can run quite happily on newer versions of compiler. The reason why Java is every developer's first love is because it is simple, object oriented, distributed, interpreted, robust, secure, architecture neutral, portable, high performance, multi threaded, and dynamic. All in one package. Java can be found running in devices like cell phones, ATMs, credit cards, parking meters, gaming console, and your bedtime teddy bear, the Delight Dynamo. Oh, sorry. My bad. I think that's the wrong link. Java is very popular for IoT and Android development. Java has evolved so significantly over the past 25 years that its versions outnumber my age and its APIs exceed the number of hairs on my head. Now that I have boasted so much about the world's most favorite programming language, let's see all of that in action. But before that, let's do the dev environment setup. Setting up an efficient Java development environment is a key to faster development. It helps streamline your coding process and makes you more productive. I will walk you through the important steps you need to set up a Java development environment. We will cover how to install the Java Development Kit, that is JDK, set up Java underscore home environment variable, download my sweet summer love, IntelliJ IDE, and configure the necessary tools and libraries. Let's dive right in. To begin, you need to install the JDK, which includes the compiler, the Java Runtime Environment or JRE, along with the Java Virtual Machine, as well as some other development tools like the debugger. Don't worry if you don't understand the meaning of all these things that I just said. We are going to see everything soon. Visit the official Oracle website and go to JDK 17. Choose the operating system and architecture that your system has. I'm currently on Mac, so I will be choosing Mac OS ARM64 DMG installer, that is disk image installer. If you are on Windows, you can choose x64 compressed archive, which is this option. The file size is 172.87 MB. Run the installer and follow the on-screen instructions. So I will just quickly download it to show you. Although I have already installed the JDK 17 version, so I won't be doing it again. When you open it for the first time, the JDK 17 installer will guide you through the installation process. Just click on continue and please take a note of the path where the JDK is getting installed on your machine. I will cancel this because I already have JDK 17. After you are done with your installation, the next step is to set the Java underscore home environment variable. If you are on Mac, open up the terminal, and by default, Mac should open up the ZSH terminal. Type the command vi tilde slash dot zshrc and press enter. Press I for insert and type export Java underscore home in capitals equals the path that you copied in the previous step where the JDK is currently installed on your machine. For me, the Java was installed under library folder, so that is the path you can see in the terminal screen. And now you can press escape :WQ to save the file. And voila, congratulations, you have successfully set the Java underscore home environment variable to the JDK installation directory. This variable is now accessible to all Java applications and tools on your system. The next step is to choose an IDE. An IDE makes coding simple and gives you various features like code editing, debugging, and project management. For this series, we will be using IntelliJ IDEA Community Edition. Go to the official page of JetBrains for downloading the Community Edition of IntelliJ. It is completely free to use compared to its paid counterpart, the Ultimate Edition. We will click on Download, which will install the G image on your local. Click on it and follow the instructions on the screen. I have it already downloaded on my system, so I won't download it again. Let me switch to it. Welcome to IntelliJ IDEA. Now we will configure it to suit our needs. Go to File on top and click on Project Structure. In the project structure, navigate to the SDK section in the Projects panel. Choose the JDK version that we have installed, which is JDK 17. For me, it is showing over here, JDK 17. If it doesn't show up for you, you can click on Add JDK folder and manually add the path where JDK is installed on your system. I will just quickly select the 17 Oracle OpenJDK 17 version. Click on OK. After this, close the project structure panel and click on New Project. I will just expand it. Enter the name as Learning Core Java and choose the location where we want to store the project. In my case, I'm storing it under the workspace directory, as you can already see. I already have this directory created, that is why it is showing me a warning. But if you haven't created it already, then just click on Create at the bottom and it will create it for you. I will just open the existing project. So this is the Learning Core Java package. So I will just open it up. In the initial project structure, we are working within the Learning Core Java folder. In Java, folders are referred as packages. Inside this folder, you will find two key packages. The first one is .idea, which contains the IntelliJ IDEA settings, and the second one is source or SRC package, where all your source code should be placed. We will talk about that in a while. Additionally, there is an external library folder, which includes all the official libraries that come with JDK 17. These libraries are essential for running your code. We will delve deeper into what all of this means in a short while. For now, that's the basic overview you need to get started with Java programming. Now that we have set up our environment, let's dive into our first Java program and explore the anatomy and structure of the code. When it comes to Java code structure, remember this mantra. In a source file, put a class. In a class, put methods. And in a method, put statements. That's the Java way. What goes inside a source code file? A source code file with the .java extension typically holds one class definition. The class represents a piece of your program, although a very tiny application might need just a single class. The class must go within a pair of curly braces and their names always start with an uppercase letter. What goes inside a class? A class has one or more methods. A method is a construct that contains statements. In the lion class, the roar method will hold instructions for how the lion should roar. Your methods must be declared inside a class. In other words, within the curly braces of the class. What goes inside a method? Within the curly braces of a method, write your instructions for how that method should be performed. Instructions, as I already told, in high-level language context, they are also known as statements. Method code is basically a set of statements, and for now, you can think of a method kind of like a mathematical function or a procedure that needs to be performed. Now that we understand the code structure, let's create a simple Java program that displays the message "Welcome to Java" on the console or terminal. Every Java program must have at least one class. Each class has a name, and by convention, class names start with an uppercase letter. In this case, the class name is welcome, and we have written it as public class welcome. Public means that this class is visible to everyone outside, and everyone can access it. Don't worry if it all sounds very overwhelming to you. We just want to write our first program so that you can get a feel for Java and you can get ramped up. We will dive deeper into these concepts in future episodes. Moving on, class implies that this is a class, of course. Welcome is the name of the class, followed by opening braces of the class. A class, as we already know, may contain several methods. When you compile the program and run it, the first thing that the compiler looks for is a specially written method that looks exactly like public static void main. The main method is the entry point where the program and the life cycle of your Java code begins. Every Java application must have at least one class and at least one method. Not one main method per class, but just one main method per full application that you are creating. An application is made up of a bunch of different classes, by the way. For now, we will focus on working with individual Java files, but don't worry, in future sessions, we will explore how different Java files can interact and work together. We will get back to the meaning of static later in this series, so just ignore it for a while. Void is the return type of the method, and in this case, it is implying that there is nothing to return from here. Main is the name of the method, which takes an array of strings as arguments, and we are calling that array as args or args. We will talk about arrays in future episodes. For now, just remember that you need to have a public static void main method at the start of your program. The method is followed by an opening brace. The next thing that is executed after the main is everything between the curly braces of the main method. Method code is basically a set of statements. Statements are nothing but instructions that we want the computer to perform. The main method in this program contains the system.out.print statement. This statement instructs the computer to display a string, welcome to Java in quotes with exclamation mark, on the console or your output device or your terminal. A string is a programming term meaning a sequence of characters, basically, similar to English. A string must always be enclosed in double quotation marks, so we have already done that. And every statement in Java must end with a semicolon, which you can also see on the screen. That is known as the statement terminator. The line that begins with a double slash is known as a comment. Whenever the compiler sees it, it ignores it because they are just for improving the documentation of code. And every brace that you open must be closed at the end. Voila! That was our first Java code ever. I hope you all are feeling at the top of the world after learning all about this, just as I am. Now that we have created our first program, let's see how to get it compiled and executed. The first step is to create a Java program, also known as source code, and save it on your disk. You can use any text editor or IDE to create and edit a Java source code file. In this particular series, we will be using IntelliJ IDEA, Community Edition. The source file must end with the extension .java and must have the same exact name as public class name. For example, the file for the source code in this case should be named as welcome.java since the public class name is welcome, where welcome is starting with a capital W. A Java compiler translates a Java source file with the extension .java into a Java bytecode file which ends with an extension .class. The command that compiles welcome.java is javac welcome.java. So this is the command for compiling your Java code. If there aren't any syntax error, the compiler generates a bytecode file with a .class extension. Thus, the javac or the Java compile command generates a file named welcome.class. To run this compiled bytecode file, use the Java welcome command. So this is the flow when everything works fine. As you can see, the result is displayed on the screen and welcome to Java is printed on your console or the terminal. However, let's say you didn't follow the syntax of Java language properly. Then the compiler will raise a syntax error and you will have to modify your Java code to fix it. A syntax error implies that you have not followed the rules of Java grammar while writing your statements. If the program fails to run when the bytecode is executed, then that is known as a runtime error. In that case, it is a long process as you must modify your source code, save it, compile it again, run the bytecode file, and then execute. And that is how Java works internally. It all looks so beautiful and fascinating, isn't it? As we already saw, you save a Java program in a .java file and compile it into a .class file. The .class file is executed by the Java virtual machine, or what we know it as JVM. The Java language is a high-level language, but Java bytecode is a low-level language. The bytecode is like assembly code instructions, but is architectural neutral and can run on any platform that has a Java virtual machine. This is one of the Java's primary advantages, that Java bytecode can run on a variety of hardware platforms and operating systems. You can execute the bytecode on any platform with a JVM. Even if your personal aeroplane has a JVM, then you can run your Java bytecode on it, provided that you own an aeroplane first, of course. JVM translates the individual instructions in bytecode into the target machine language code one at a time rather than the whole program as a single unit. Each step is executed immediately after it is translated. In computer terminology, we call such a thing as an interpreter. We talked so much about how to write our first program and what is its code structure and anatomy. But where is the official documentation of syntax or grammar for Java programming language? Computer languages, as we know, have strict rules of usage or grammar. If you do not follow the rules while writing a program, the computer will not be able to understand it. The Java language specification and the Java API defines the Java standards. The Java language specification is a technical definition of the Java programming languages, syntax, and semantics. You can find the complete Java language specification at this link. As you can see, this is the official Oracle Java documentation defining the Java language and JVM specifications for each version of Java. We are using Standard Edition 17 for the Java programming language, and you can view its official doc by scrolling down either in HTML or PDF format. As you can see, this is a 848-page document talking about the grammar, lexical structure, and semantics of the Java programming language. A short disclaimer. To fully understand this document, you might need to attend a compiler design course and develop an understanding over what are context-free grammars or CFGs, lexer or tokenizer, semantic analysis, and how does a compiler work in itself. Moving back. Next, we have is the application programming interface, also known as Java library, which contains predefined classes and interfaces for developing Java programs. The API is still expanding. You can view the latest version of Java API from this link. This is the official doc for the Java Standard Edition 17 specification. You can see several modules defined here, each having their own unique purposes. Remember, when a few minutes ago we were setting up our environment in IntelliJ and I pointed out the external library section, well, this page is the official documentation for all those libraries that Java 17 provides. You can go through this at your own discretion. Next in line that we have is JDK, JRE, and JVM. Let's understand all three of these with an illustration. Starting from the outside of the box, JDK or Java Development Kit is the full package. The JDK consists of a set of separate programs where each of them can be invoked from a command line, and it is used either for compiling, running your Java program, debugging your Java program, or testing your Java programs. For example, to compile, you can use the javac command as we already saw. And for debugging, you can use -x debug flag as shown in this diagram. One such program out of JDK, as I already told, JDK has a lot of programs inside it. One such program is JRE, that is Java Runtime Environment. It is a program that is specifically used for running Java source code. It provides various set of libraries and other files to JVM at runtime as required. The libraries that we just saw, the external libraries associated with Java Standard Edition 17, this is the external libraries that GRE provides. A user can install only GRE and not JDK if he just wants to run the Java code. I repeat, only for running the Java code and not compiling or developing it, you can just install GRE for that purpose. JVM is the third and the most important part of the Java Development Toolkit. JVM is a subpart of GRE and it stands for Java Virtual Machine. As we already saw, it is responsible for running your translated bytecode file with .class extension by interpreting them line by line and executing them on the screen. Now that we have covered a lot of ground, let's see our first Java program in action. Let's switch to IntelliJ IDEA Community Edition. As mentioned earlier, the source code should always be placed within the source or the SRC package. To create a new Java class, right-click on SRC, select New, and then choose Java class. Name the class as Welcome, and press Enter for Windows or Return for Mac to create a new Java file. Since I have already created the file, I won't be repeating the process, and I will open it by double-clicking on this file. To compile and execute the program, simply click on the green play button at the top right corner of the screen, and bam! The output is displayed on the terminal, or what we call it as console. As you may have noticed, a new orange colored folder labeled out was automatically created on the left hand side while we did this process. Inside this folder, you will find the welcome.class Java bytecode file. When you click the green play button, IntelliJ first invokes the Java compiler to generate the welcome.class file and stores it inside this out folder. IntelliJ then automatically triggers the JVM to execute this .class file and display the output on the console. All these processes are handled seamlessly in the background. Congratulations! You have just written and executed your first ever Java code. Take a moment to savor the experience and let all those feelings sink inside you. Ah, we covered a lot in this episode. For those who are feeling a bit nauseous, here's a quick summary for you. Every Java source file must end with a .java extension, and the file name must exactly match the public class name. A compiler checks the syntax and semantics of the Java code and produces a bytecode file with .class extension at the end. JVM, or Java Virtual Machine, executes these bytecodes line by line. All of this comes packaged or bundled inside Java Development Toolkit, which we also know it as JDK. Also, don't forget, in order to run a Java program, it must have an entry point, which is defined by the public static void main method. Lastly, add comments at appropriate places in your code so that you don't forget what you wrote a day ago. And that's it for this episode. In the next episode, we are going to talk about things that we can write inside the main method as part of elementary programming. So thanks again for watching, and please like, share, and subscribe for more Java content from me.